everybody. Today we are going to discuss the conditional expectation in case of bivariate distribution. What is conditional expectation? We all know the conditional distributions and the expectation of a variable in the conditional distribution is called the conditional expectation. Therefore, if we have a two-dimensional joint random variable x comma y, and in that bivariate distribution, we can consider the distribution of the conditional distribution of x given y is equal to y small. Particularly, if it is a discrete case, we can consider y is equal to yj. All right, and we know the corresponding probability mass function in case of discrete conditional distribution. The corresponding probability mass function of x is represented by f I given j. And what is this f I given j? We already defined this f I given j. We proved this result in the previous lectures that f I given j is equal to f I j. That is the joint probability mass function divided by f y j, the marginal mass function of y. So these are actually the conditional mass function of the distribution of x given y is equal to yj. Now in this distribution, when it is given that y is equal to yj, in that case the expectation of this kind of function g of x comma y, expectation of this kind of function g of x comma y given y is equal to yj is actually defined in this way, that summation, as actually you see whenever this y is equal to yj is provided, therefore the only unknown variable is x. So over here we are actually computing the expectation from the conditional distribution of x. All right, so summation should be taken over I. Theoretically I should vary from minus infinity to infinity, and over here in place of g x comma y, we are putting g of xi comma yj, because over here y is already given to be equal to yj, and as because it is a expectation of x, and therefore we are actually putting xi in place of capital X. And this is the conditional mass function of x given y is equal to yj. All right, and we all know that this if I given j, this can be written as equal to f ij divided by f yj. Therefore, if we put this relation over here in place of f ij, in that case we get this type of result, summation gxi yj f ij, that is the mass function of the bivariate distribution, divided by f yj. You can also write this f yj by f dot j, that is actually the marginal mass function of the distribution of y, mass function of the distribution of the marginal distribution of y. Okay, so in this way we are defining the expectation of gxy when y is equal to yj. And similarly, you see, you can also define the expectation in case of conditional distribution of y given x is equal to, say, xi. Then how can we define this one? We can write expectation of this kind of function g of x comma y given x is equal to xi. How can we define this one? We shall have to define it in this way. You see, y x is equal to xi is already provided. Therefore, it is actually the expectation obtained from the distribution of y. That's why we should write summation over j. Theoretically, it is varying from minus infinity to infinity. In place of x and y, we are just writing xi and yj. So we shall have g of xi, comma yj, and this should be multiplied by the conditional by the mass function of the conditional distribution of y, and that is actually written as f j given I. And we know this f j given I, this f j given I can be written as equal to, you see, f j given I, this can be written equal to f I j divided by f xi, or this can also be written in this way, f ij divided by f I dot. So if we apply these results over here, if we apply these results over here, let us put this expression in place of f j given I. Okay, in that case, what we have, in that case, this expression can be written as equal to the summation over j, summation over j. J is theoretically varying from minus infinity to infinity. G xi, comma yj multiplied by f I j divided by f I dot. So in this way, we can define the expectation in case of conditional distribution of y given x is equal to xi. All right. Now, in this kind of distribution, these were the discussions for discrete distribution. These were discussions from discrete distribution, and in case of discrete distribution, if we put if you particularly compute expectation of x given y is equal to yj, in that case we will get what you call is the conditional mean of x. So by this type of definition, what we get the conditional mean, would be this type of expression: expectation of x given y is equal to yj, and in that case, of course, in place of x we shall have to put xi, and the remaining portion is exactly same. So summation over I xi f ij divided by f dot j. This is called the conditional mean of x, and this is designated by m suffix x given j. M suffix x given j. This would be the conditional mean of x. Similarly, if we want to find out the conditional mean of y, in that case, this conditional mean of y would be written in this way: fy given I. So its definition would be is equal to expectation of y given x is equal to x. So in this way, we can find out the conditional mean of y, and exactly in the similar fashion, we can define the conditional mean of y. Next, after defining the conditional mean, we need to define the conditional variance. You see, generally, what is the definition of variance? Variance is defined in this way: sigma square, that is the variance. Variance is equal to expectation of what x minus corresponding mean in its whole square. Okay, so this is the definition of variance. Now, if you consider the conditional expectation, that means if we put the condition that y is equal to yj, in that case, in place of m, we shall have to put the mean, that is actually the mean of the corresponding conditional distribution, that is actually this x given j. So we shall have to write x given j. All right. and that would be the conditional variance, and that's why this is also written as sigma square suffix x given j, something like this. So this would be the variance of the conditional distribution of x given y is equal to yj. Similarly, we can also define the variance in the conditional distribution of y. So what would be the corresponding definition? The corresponding definition would be is equal to, suppose, y minus the corresponding conditional mean. So it would be in y given I, its whole square, and the given condition is that x is equal to xi. All right, so this would be the definition of conditional. This would be the definition of the conditional variance of y, and it should be designated as sigma square y given I. All right, under the condition that x is equal to x. All right, so in this way we can define the variance for the conditional distribution of y given x is equal to x. So these were all definitions in case of discrete distributions. Now let us move to the corresponding definitions in case of conditional distribution. Now in case of conditional distribution, you see, if we define this type of conditional mean, in that case what we need to do, we need to integrate in place summation. Of course we shall obtain integration with respect to x, of course. So integration from minus infinity to infinity, integration from minus infinity to infinity, g of x comma y, and over here we shall have to consider the conditional density function of x given y is equal to small y. All right, and this is designated by f suffix x within bracket x given y. Now, what is this expression? This one, this f suffix x within bracket y given sorry, x suffix x within bracket x given y. This is actually defined in this way: the density function of the bivariate distribution divided by the corresponding marginal density function of y. Okay, so if we put this expression over here, if we put this expression over here, in that case this expectation can be defined, can be written in this way: that integration from minus infinity to infinity g of x comma y multiplied by f of x comma y dx divided by the marginal density function of y. And in this similar fashion, we can also define the expectation of expectation from the marginal density, expectation from the conditional density function of y. So if we want to define this one, how can we define it? We can define this one this way: that suppose x is equal to small x is provided, it is given, and in that case if we want to find out the this type of expectation of g of x comma y, given that capital X is equal to small x. So capital X is equal to small x is actually a given condition. Therefore, we shall have to integrate with respect to y. Therefore, it should be integration from minus infinity to infinity g of x comma y. And over here we need to write the conditional density function of y. So fy y given x, and integration is to be performed with respect to y. And we know that this fy y given x, this is actually, this can be written this way: the density function, the joint density function fxy divided by the marginal density function of x. Okay, so if we write this expression over here, in that case this result can be, this expression can be written as the ratio of integral from minus infinity to infinity g of x comma y if x comma y dy divided by over here we have to write the this marginal density function of x. So in this way we can define the conditional expectation from the conditional distribution of y given x is equal to small x. All right. Now let us define the conditional mean. You see, in place of this function g, if we put x, in that case we will get the conditional mean. So this conditional mean will be defined in this way: integration from minus infinity to infinity. Just in place of the function g of x comma y, we are just putting over here x, and the remaining part, as per this formula, the remaining part is exactly same as per this formula. And this is in case of continuous distribution, this is defined and this is represented as mx of y. We can also represent it in this way: mx given y. However, we prefer this notation because later on we will find that this type of function actually represents a special kind of curve that is called the regression curve. Hopefully we will discuss this regression curve at the end of this lecture. Now we can also define the conditional variances. The conditional variance, how to define the conditional variance? You see, this is actually the conditional mean of y given x is equal to small x. And how to define the conditional variance? You see, the variance is defined in this way: sigma square. So that is actually is equal to expectation of x minus corresponding mean, its whole square. Okay. Now in case of conditional distribution, if it is given the condition that y is equal to small y, by the way, remember that in case of continuous distribution, y is equal to small y, the meaning of this event will always be represented in terms of limit that delta y tending to 0. This event would represent actually the limiting event of the fact that y less than capital Y less than or is equal to y plus delta y. We already discussed this result in the previous lectures. Anyway, so let's continue over here. And if y is equal to small y, this condition is provided. In that case, over here, this mx of y should be written. I am writing this kind of condition: mx given y, and in that case we can write sigma x given y, or sometimes there is also written in this way: sigma square x of y. So we have this type of notation: sigma square x of y, that is actually the conditional variance of x given y is equal to small y. So this is the definition of the conditional variance of x given y is equal to small y. Similarly, we can define the variance of y given x is equal to small x. This is actually the definition of the conditional variance of y given x is equal to small x. And we all know that if capital X and capital Y are independent, in that case, this kind of marginal density function, this kind of conditional density function becomes equal to the corresponding marginal density function. So the conditional density function of X would become is equal to the marginal density function of X, and the conditional density function of Y will become is equal to the marginal density function of y, and as a consequence the conditional mean would become is equal to the marginal mean, and therefore the conditional mean of x becomes the marginal mean of x, the conditional mean of y will be the marginal mean of y. Similarly, the conditional variance of y conditional variance of x will become is equal to the variance of x obtained from the marginal distribution, and conditional variance of y will become equal to the variance of y obtained from the corresponding marginal distribution. However, if they are not independent, if capital X and Y are not independent, all right, if they are not independent, in that case we can prove, we are going to prove this result actually. In that case we can prove that expectation of the conditional mean, this type of expectation of conditional mean of x All right. This type of expectation, that would be is equal to this mx. And similar result holds for uh, the distribution of y as well. So let us prove this result first. Over here, you see expectation of this my of x. So let us prove this result, that would be is equal to the mean of y, and expectation of mx of y, that would be is equal to the mean of x. We are proving the result for the distribution of x, and similar result can be proved for the distribution of y. So expectation of myx, what is this? This would be is equal to, you see, this is actually a function of x. Therefore, integration should be performed with respect to x. And as because this is a function of x, therefore, marginal distribution of marginal density function of x should be written over here. And this my of x, the corresponding real expression would be equal to my within bracket small x. Alright, so this expectation should be written in this type of integral form. We are presenting this one in terms of continuous distribution. You can also put this result in case of discrete distribution as well. Anyway, so this my of x, this my of x, its expression is equal to this type of expression, expectation of y given x is equal to small x. And what is this? This expectation is actually this type of integral from minus infinity to infinity y multiplied by the corresponding conditional density function, because you see this is actually conditional expectation. So if it is a conditional expectation, we shall have to multiply by conditional density function. If it is ordinary expectation, we shall have to multiply by marginal density function. All right. So over here, if you can rearrange these terms, and rearranging, we can write it as the double integral from minus infinity to infinity to minus infinity to infinity, and y is there. Now these two expressions, you see this is the marginal density function of x. So if x multiplied by this marginal density function of y, multiplied by this conditional density function. I'm sorry. So multiplied by this conditional density function of y, fy of y given x, and these two together, the product of this expression becomes is equal to the density function of the joint bivariate distribution. So we write it as f of x comma y, and this is equal to the mean of y. By definition, this is actually the mean of y obtained from the bivariate distribution. So finally, this can be written as expectation of y, that is equal to n suffix y. All right. So we put this result that expectation of mx of y is equal to mx. We put this result, expectation of my of x is equal to my. We can also put this result, expectation of mx of y is equal to mx. Okay. So this one result. The next result that I am going to put over here is that expectation of this y minus gx whole square, this type of expectation is minimum when gx is equal to the conditional mean my of x. All right, and you see, this would be very much similar to the result in case of function of single variable. We had a result that expectation of x minus a whole square. Over here, a is a function, but in our case, this g is actually a function of x, and there a was a constant. All right. So expectation of x minus a whole square. This expectation is minimum when a is equal to the mean of x. And this type of result was there in case of function, in case of probability distribution of single random variable. And in this kind of bivariate distribution, we are going to prove a similar result, that expectation of y minus gx whole square. This is minimum when this function gx, about which the expectation is computed, when this function gx becomes is equal to my of x. We are going to prove this result. So let us compute this expression of y minus gx whole square. You see, this expectation of y minus gx whole square, This is actually function of two variables. Y is there, X is there. So we shall have to compute this expectation right from the joint distribution, and therefore we can write this kind of double integral. Over here, in place of this type of random variable, we shall have to write the corresponding real expression, that is y minus gx whole square, multiplied by the density function of the corresponding bivariate distribution f of x comma y dx dy. And this expression, this density function of the bivariate distribution, this density function can be written as equal to the marginal density function of x multiplied by the conditional density function of y given x is equal to small x. And you see this type of expression, this type of integral can be written as the integral of y minus gx whole square multiplied by this type of additional density function integration with respect to y, and after that whatever we shall get, that should be x, and that should be integrated with respect to x. So that should be multiplied by fx, and then it should be integrated with respect to x. Now you see this expression. This expression is actually the expectation of y minus gx whole square given x is equal to small x. Why we obtain this type of expectation? Because over here we are actually considering this conditional density function of y given x is equal to small x. That's why we are writing this result, x is equal to small x over here. So we shall get this type of expectation, and that would be multiplied by this marginal density function of x. Now let us try to decompose this expression y minus gx whole square, and after decomposing this expression, we shall put x is equal to small x, and finally we shall compute the expectation of x. How to decompose this y minus gx whole square, this type of expression? Let us write this y minus gx whole square is equal to this. We are just subtracting y of x. This is the conditional mean of y given x, given capital X is equal to small x, and then adding this one multiply minus gx, and so we have this can be written as a plus b whole square. This type of form. This is our a. This is our b. So a plus b whole square formula is to be applied. So this is our a square plus b square plus twice ab. Now we put x is equal to small x. We put the condition that x is equal to small x. So if we put x is equal to small x over here, if we put x is equal to small x, on the left we just put, considering this type of conditional event by putting x is equal to small x, and then in the first term, in this second term, and in this third term, we shall have to put x is equal to small x. So we shall get this type of conditional events by putting x is equal to small x. And over here you see that x is equal to small x. Over here this g of x, if we put x is equal to small x, then in that case this can be written as g of small x. Similarly over here if we put x is equal to capital X is equal to small x, in that case in place of g of capital X we have g of small x, something like that. Okay. And now we take the expectation on both sides. So expectation of this term is equal to expectation of this first term plus expectation of this second term plus expectation of this third term. So we consider this type of expectation. So we have this expectation of first term, then the expectation of second term, and then this expectation of over here. This should be capital X. Okay. And then we shall have expectation of this third. All right. Now you see over here this quantity after putting capital X is equal to small x does not depend upon what is actually expectation of what expectation of y. We are computing the expectation obtained from the marginal the conditional density function of y. So we do not have any expression of y. So this expression is actually independent of capital Y. That's why this quantity should be treated as an independent quantity or a constant quantity with respect to capital Y. So expectation of a constant quantity is that quantity itself. That's why we can directly write this expectation over here. Hmm? Again, this expression involves capital Y, but this factor does not involve capital Y. So this factor can be taken outside this expectation. So we put this over here outside this expectation, and inside the this bracket, inside the bracket, we have expectation of y minus myx, even capital X is equal to small x. And further, this expression can be decomposed further by this type of term, that expectation of y given capital X is equal to small x, and then expectation of myx given capital X is equal to small x. This is actually our conditional mean of y given x is equal to small x. And what is this? This is actually constant term with respect to y. So expectation of that constant term is that the constant term is itself. So this will be the value of the second expectation. And you see over here, this factor, the value of this factor, these two terms will get cancelled, and the value of this factor is equal to 0. So effectively, the contribution obtained from the third term becomes equal to 0. So we shall effectively have the first term and this second term. Okay, and from this result, it is clear that this left hand side or this entire right hand side would be minimum when this g of x would become is equal to this m suffix y of x. Therefore, we can say that yes, this type of expectation is minimum whenever g of x becomes equal to my of x. Or in other words, you see, and this type of expectation is exactly same as this expectation. So if this expectation is minimum when this g of x is equal to this my of x, in that case you see this second term would also become is equal to 0, and this would be minimum when g of x is equal to my of x. Therefore, we can say that the entire expression, this entire expression would be minimum, or in other words, this entire integral or this entire expectation is also minimum when this function g of x becomes is equal to the conditional mean of y given capital X is equal to small x, conditional mean of y on x. Okay, this is called the conditional mean of y on x. Now let us try to find out the conditional mean in case of bivariate normal distribution. Let us try to find out the conditional mean in case of bivariate normal distribution. You see, we already discussed this bivariate normal distribution in the previous lectures. Let me just recall in first forward fashion. This is the joint probability mass function for bivariate normal distribution, and these are the marginal density function of x and the marginal density function of y. Now, if we are interested to find out the conditional density function of x given y, so in that case, we shall have to divide this joint density function by the marginal density function of y. And after division, we proved that the conditional density function can be written in this way: 1 by root over of twice by sigma x into root over of 1 minus rho square e to the power of minus 1 by 2 into 1 minus rho square into this type of expectation, this type of expression. Okay, and this is the same expression written over here. And now you see this expression can also be written in this fashion. We can take this sigma x common and take it outside this bracket. So we shall have sigma x square, and within the bracket we shall have x minus mx from this first term minus rho into sigma x by sigma y into y minus my whole square. Okay. Now, if this expression, this sigma x into root over of 1 minus rho square, if it is written as sigma, all right, and this expression x minus whatever we have, this expression, if it is written as equal to capital M, in that case you see this density function can be written in this way. Say over here fx x given y, that is the expression of this left hand side. This can be written as 1 by twice pi and this remaining, this expression is actually is equal to sigma, and over here this exponent can be written as 1 by minus 1 by 2 sigma square into x minus n whole square. This is actually the density function of a normal distribution with parameter m and sigma. Okay, with parameter m and sigma. Therefore, we can say that the conditional density function, the conditional distribution of x is also a normal distribution with parameter m and sigma. Okay, so what is m? This is the conditional mean m, all right, and this would be the conditional variance. And over here, this is conditional mean. In that case, we have the the next idea, that is called the idea of regression curve of y on x. All right. What is this regression curve of y on x? Let me write it over here. The regression curve of y on x. Regression curve. Regression curve of y on x. First, we are defining regression curve of y on x, and in the similar fashion, we can also define regression curve of x on y. Okay. Now, you see what is the regression curve. We already, in case of in any bivariate distribution, you see we can consider the marginal, we can consider the conditional mean m y of x. This is the conditional mean of y given capital X is equal to small x. Okay, and what is this? If we change the values of x, it will ultimately describe a curve. This curve y is equal to y of x. This curve will be called the conditional curve of y on x. So what is this? Y is equal to this one. You see, if you consider a bivariate distribution, say if suppose this is the value of x, in that case we, for this value of x, we will have certain value of m y of x. So this type of value would be there. Now if we change this x from this position to this position, all right, in that case it might happen that the value of myx is changing, and so for different values of x, we will get a curve, and this curve, this type of curve, this is actually the curve of this my of x. This is called the condition, this is called the regression curve of y on x. And we already proved this result so far, that this type of expectation of y minus g of x, we obtained this type of result, that y minus g of x whole square. This type of whole square. This is minimum. So we obtain the minimum value of this result when this function g of x becomes is equal to m y of x. Okay. So geometrically, what does it mean? Geometrically, it means, suppose for this, suppose this is the value of x, and we may have the value of y, something like this. This might be the value of y. This quantity, this distance might represent the value of y. So this difference in between, you see, this is actually the this much. Let me draw it over here. This much would be the value of this my of x. Okay, and this difference refers to y minus my of x. So in place of this type of curve, in place of this type of regression curve, if you consider any other curve, say this type of curve, any other curve, and suppose this is the curve of the function gx, and in that case this type of height, that is actually called the deviation of y from gx. Okay, deviation of y, deviation of y, deviation of y from g of x. This property says that this deviation would be minimum. This deviation would be minimum when this g of x becomes is equal to this conditional curve of y on x. Alright, so this is the geometric interpretation of the property. That's why this property, what we have discussed so far, this property is called the minimum property. Over here, this property, sorry, just a minute, this property, this one, that expectation of y minus gx whole square is minimum when gx is equal to myx. This property is called the minimum property, and the geometric interpretation of the minimum property is that the deviation of y will be minimum when this deviation is taken about this regression curve of y on x. All right. So this is the main importance of regression curve. And over here, similar to the regression curve of y on x, we can also compute the regression curve of x on y. Regression, sorry, regression curve of x on y. What would be the regression curve of x on y? X is equal to mx of y. This would be the regression curve of y. So we got two regression curves of y. Now we are going to compute the regression curves of x on y and y on x in case of bivariate normal distribution. We already proved this result that in case of bivariate normal distribution, the conditional mean, the conditional mean of y on x, conditional mean of y on x, we already proved over here that the expression of conditional mean of y on x is this type of expression. This is the expression of conditional mean of this is the conditional mean of x on y. All right, this is the conditional mean of x on y. So if we consider the conditional mean of x on y, the conditional mean of x on y, what is this? The conditional mean of x on y. Let me just write the expression mx plus rho into sigma x by sigma y. So this is equal to mx plus rho into sigma x by sigma y multiplied by y minus myx. So we have y minus my, so simply y minus my. So what would be the regression curve? Regression curve of x on y. As per the definition, the regression curve of x on y is equal to this type of term. X is equal to mx of y. So we just write this entire expression over here is equal to mx plus rho into sigma x by sigma y multiplied by y minus my. And you see this expression, this equation, it is actually can be written in this way: x minus mx divided by sigma x, that is equal to rho into y minus my divided by sigma y. Alright. So this would be the regression curve of y on x. And what would be the regression curve of x on y? All right. Regression curve of x on y. What would be the regression curve of x on y? We can similarly prove that regression curve of x on y can be written in this way: y minus my divided by sigma y, that is equal to rho into x minus mx divided by sigma x. So this would be the regression curve of x on y, and this is actually the regression curve of y on x. You can observe that both of these two equations actually represent two straight lines. So over here, in case of bivariate normal distribution, the regression curves are actually two straight lines, and you can compute the gradient of the straight lines. Over here, you see this is rho is actually the gradient of the regression curve of x on y, and what would be the gradient of this regression curve of x on y. This is actually the regression curve of y on x. Sorry, I made a mistake. Hmm. Let me just rectify this mistake over here. We should actually write it in this fashion. We should write y on x. Okay, regression curve of y on x. Sorry for the inconvenience. So over here, in case of regression curve of y on x, we can now write that gradient of the regression curve. All right, gradient, gradient of the regression curve of y on x. What is regression curve of y on x? The regression curve of y on x is equal to y minus my divided by sigma y is equal to rho into x minus mx divided by sigma x. So rho is actually the gradient. This is actually the gradient. And if we consider the regression curve of x on y, in that case, what we shall have, the equation of the curve is x minus my x minus mx, sorry, x minus mx divided by sigma x, and that is equal to y minus my divided by this sigma y multiplied by rho, and this rho can now further be shifted over here. And therefore we can observe that this 1 by rho is actually the gradient of the equation curve of x on y. Okay, so these are some results on in case of bivariate normal distribution. Now, to finish this lecture, let us discuss a technique that is called the least square regression curve. Least square regression curve. Least square regression curve. Regression curve is actually motivated by the minimum property. In the minimum property, what we have studied is that this type of expression y minus g of x, we have studied that y minus g of x whole square, this is minimum, this is minimum when this g of x is equal to the regression curve of y on x. Now, in place of this g of x, basically this g of x can be any kind of continuous function. But if this g of x particularly becomes a polynomial, that means suppose this g of x, or in terms of real variable, if we write g of x is equal to a polynomial, something like this type of polynomial, say c0 plus c1 x plus c2 x square, etc. dot 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 plus cn x to the power of n. In that case, we can consider this c0, c1, c2, etc. as the parameters of this function g. And in that case, what we need to do, we need to minimize this expression y minus g. We can write this expression now as equal to g of x along with these parameters c0, c1, etc. Okay, so we shall have to minimize this expression g of x comma c0 comma c1, etc. Actually, we need to find out the values of this parameter for which this expression is minimum. We need to find out the values of these parameters for which these expressions are minimum. And in that case, you see this expression is, let us designate by s. This expression, this s, would actually be a function of these parameters. If capital X and capital Y are provided, in that case, this would be the function of these parameters c0, c1, c2. So this should be minimized, and that minimization can be achieved by the method of least square. That's why this technique is called the least square regression curve. And in order to prove this result, we can now say that over here, we can now say that if we consider gx is equal to a linear expression like c0 plus c1x, this type of expression, then we need to compute the corresponding values of c0 and c1, so that this expression, expectation of y minus gx whole square, this expression, or in other words, this expression, expectation of y minus c0 minus c1x whole square, becomes minimum. Alright, so this s now becomes a function of these two parameters c0 and c1, and in order to minimize this function, we can say that this partial derivatives must be equal to 0. So you see, if we differentiate this expression under integration with respect to c0, we will have this type of expression 2 into y minus c0 minus c1x multiplied by this minus 1 f of x comma y dx dy, and that would be is equal to 0. And if we expand it, forget about this minus 1, we can take it outside the integral and cancel this one. So if we expand it, we will get this type of expression. So expectation of we have integral of y multiplied by f of x comma y dx dy, that would give us expectation of y, that is this type of expectation. Then expectation of altogether we will get the expectation of y minus c0 minus c1x, and that can be further decomposed in this way: expectation of y minus c0 minus c1 into expectation of x is equal to 0. And that ultimately gives this type of relation. Let us designate it by equation number 1. And for the second parameter c1, we need to differentiate this expression capital S with respect to c1, partially with respect to c1, and that the derivative would also be equal to 0. And by this similar computation, we will get this type of relation, that expectation of xy minus c0 into expectation of x minus c1 into expectation of x squared. Now we are going to compute the expression of this expectation of xy and the expression of this expectation of x squared. You see, we know the covariance of xy is equal to expectation of xy minus mx into my, and we have a relation that rho is equal to covariance of xy divided by sigma x sigma y. So in place of this expression of covariance, we can write this covariance of xy is equal to rho into sigma x sigma y. So we have this relation, rho into sigma x sigma y is equal to this expectation of xy minus mx in y. So we have this result, and from this result we can compute the expectation of x into y. Similarly, we know that sigma x square, that is actually the variance, sigma x square is equal to expectation of x square minus mx whole square. So this expression becomes is equal to expectation of x square So we get the expression of expectation of x square is equal to sigma x square plus mx whole square. So now, if we now put these expressions of expectation of xy and expectation of x square over here in this equation number 2, we will get this type of relation. And now we can solve this equation number 3 and this equation number 1. And after solving these equations, we get the value of the C0 and C1. And let us designate this expression of rho multiplied by sigma y divided by sigma x by beta y x, and this is called the regression coefficient of y on x. And let us suppose that this is equal to C1 star, and the value whatever we get, that is, let us call it let us call it C0 star. So what we get, the values of C0 and C1 by the method of least square. Alright, what we get actually the values of C0 and C1 by the method of least square. Now, what was the regression line? We took y is equal to C0 plus C1 into x. Alright, so now if we put C0 star in place of this C0 and C1 star in place of this C1, we will get the expression. What was C0? C0 was equal to this type of expression, my minus rho into sigma y by sigma x into mx. And you see, we took this expression as equal to beta y on x. So we took this expression beta y on x, beta y on x, that is equal to rho into sigma y divided by sigma x. So this expression can be written as my minus beta y x. Sorry, I could not complete the expression. This is actually C0. This is the expression of C0 star plus what was C1 star. C1 star is equal to rho into sigma y by sigma x multiplied by this x. Okay, so multiplied by this x. All right, and therefore this expression can be written as my minus rho. In fact, this rho into sigma y by sigma x, this can be written as beta y on x multiplied by mx plus this one again beta y on x multiplied by x. So what we get is that we can write y minus my, that is equal to beta y on x multiplied by x minus mx. And further, if we put the expression of this beta, in that case this expression can be written as y minus myx divided by sigma y, that is equal to rho into x minus mx divided by sigma x. So you observe that in case of this is the same expression of the regression curve of y on x in case of bivariate normal distribution. Although this method of least square was deduced for any arbitrary distribution, but from this result we can say that particularly in case of bivariate normal distribution, we can say that regression curve of y on x coincides with this line obtained from the method of least square. And this is called the regression line of y on x. This is called the regression line, as because it is a straight line. You see, this is a straight line. Okay, so this is called regression line regression, not curve, line. All right, regression line of y on x. And over here we are I'm keeping one result for your homework to find. I am keeping one result as a homework to find regression line of x on y. I am keeping this result as a homework for the students. So that's all for this lecture. Thank you for being with us.